Bonjour, Recon. Hello, and welcome to my talk. I'm really excited to be here. Yeah, like I said, I've been coming. I think my first Recon was in 2008, and it's my first time speaking. So I'm just really excited for the privilege to do that. And my handle predates Ethereum. It's not about the Ethereum virtual machine. Sorry for the confusion. So what I'm going to be talking about today is chopping up embedded binaries into their original object files. That's the Pirate's Cutlass reference, and thereby extracting the software architecture. If you're a x86 person, a malware person, stick around. I work in the embedded space, but I think this has a lot of applicability there too. So I used to be a Windows internals guy, low-level x86 guy. Ended up in the embedded world. We do a lot of work at APL where we have government sponsors come to us and they say, we've got this commercial device that we want to put in this tactical network, or we've got this commercial device that we already put in this tactical network. That's always a fun briefing. Can you tell us, is this a problem? Is it secure? So that's kind of the space I work in, vulnerability analysis in embedded devices. I spent a lot of time, even just sitting at Recon, looking at folks doing research in call graph visualization, right? So I list a couple of talks here that have been here at Recon. Folks looking at ways to look at a program as a large call graph and visualize it. But I'm often sitting there thinking, we should be able to cluster these call graphs and extract, in an automated way, and kind of extract program information about it, automatically. I feel like finding the software architecture, when we're analyzing a new device, finding that software architecture is kind of a critical piece, and the faster that we can get it, the faster we can get results. So this is a quick slide that's kind of just some overview of what kind of the RTOS and embedded space is like, especially if you're kind of from an x86 background. You can think back to if you were here for Travis's talk on the Good Watch, that sort of a development environment is often kind of what we're dealing with. So what we have usually is a microcontroller or microprocessor running a single, fully linked program. A lot of these nowadays have flash on die, so you'll have a microcontroller core and the flash all in one die or package. So you've got one address space, and if you're a Windows person, you can think of this, it's kind of like, imagine you have the Windows kernel system libraries and a couple of user applications, and they're all put into one program and they're linked together. So you get rid of all of your import and export tables, all your symbols, and you just have functions calling the functions that they need to call. That's kind of what we're usually dealing with. So we're used to dropping this into IDA, and we get that dreaded, here's 10,000 functions. We get a nice clean disassembly, 10,000 functions, and no library matches. Nothing that we've seen before. You'll get these gigantic nasty call graphs because you're looking, when you look at a call graph, you're looking at a user space all the way down through libraries into the kernel, all there. For RTOSes, they're usually distributed. If your company is going to sell a product with an RTOS, you either license the source from the company and then compile it with your program and link it together and put it in the device, or you license object files and you compile your code, link it with the object files, and you create your firmware. There's no, most of the time there's no symbols. Sometimes we get, debug prints. Often that's like, okay, there's, maybe we'll see debug prints in one area of the program or something like that. There's also there's just a gazillion RTOSs out there. And RTOS is really just kind of it's just sort of a way to handle switching execution between different threads on a processor, sort of sharing execution time and handling message passing back and forth between the threads. So there's a lot of people who have implemented that, and there's a lot of them out there. So we're constantly coming across some RTOS that we've never seen before. This is a quick diversion and talking about the process of automating RE and kind of the research, just the kind of the state of the research in automating RE. It's something I'm really interested in, and if you're interested in sort of RE automation, I'd love to talk to you afterwards. We're kind of struggling, I think, in research right now to do sort of meaningful machine learning and things like that on code for a number of different reasons. I think one of the reasons is we're not necessarily taking into account how reverse engineers work. I think when we're reversing, we're working on at least these 4 different levels, and when we're reversing, we're not just trying to disassemble or try to get some code to make sense. We're really translating these different artifacts, these different levels into our our native language, right? We're translating between code and language. Context is key, and I think that's kind of a part of why we're struggling to get traction there. Back to what I'm talking about, I kind of noticed that we don't really have anything going on kind of in the functions up to libraries level. There hasn't been really any work there. So that's kind of the place I decided to focus. So the problem is what I call it the CodeCut problem. And so just think about, if you're developing, this is true if you're developing any kind of large C program, but so, and we're generally pretty much always dealing with C or C++ in the embedded space. So you're writing multiple different source files, right? And when you compile them, they get compiled into object files, and you link them into your full program. When the linker does that, generally the linker just takes your object files and just linearly concatenates them. It just sticks them all together into your program. So your binary sort of looks like the stack of object files that you gave the linker. So the problem statement is, so given the call graph information for my large binary, can I recover the boundaries of the original object files? The reason that I pose the problem this way is that I want it to be architecture independent. I want it to basically run on anything that you can disassemble, anything that IDA works on, anything that any other disassembler works on. Generally, you can pretty easily extract the call graph. I also want to point out here that there's sort of some inherent ambiguity here. When you when you link, you lose all of that information about the names of the functions and all this stuff. So you're never going to be able to get a 100% solution or solution that's going to perfectly recover your object files. And you're also, what you're trying to do here is find clusters of functionality. So if the developer organized their code, well, if it's well architected, then that should more or less, correspond to the object files. But maybe, maybe not. You're kind of at the mercy of the design of the developer, is what I'm trying to say. So I'll say before I get into this, we did a bunch of work, and I had folks working on approaching this problem with graph theory algorithms that are out there, and we didn't get a lot of traction, didn't get a lot of progress. Graph theory algorithms are pretty inefficient generally. Like, they're some of the ones we've tried are like order n cubed. When you're dealing with a large program, it just blows up. And so we had some success doing it on like really small data sets, but didn't really get anywhere. So I started thinking about, can I approach this problem as a numerical problem? It's still a graph problem, but can I approach it, as just a numerical problem of segmenting, looking at the program as a number line and segmenting it that way. So this is the concept I came up with. So I call it local function affinity. So okay, back to our embedded developers, we've got these, bunch of C files in our build. So imagine this is your first C file. We're going to eliminate external calls. So I'll kind of punt on explaining how I do that in the binary for right now. But let's just say if we eliminated the external calls and we look at the directionality of calls within the file. So at the beginning of the file, calls are going to be in the positive direction to functions later on in the file. And I'm going to see directionality of the calls switch to the negative direction towards the end of the module. Okay. So the idea is, can I create a numerical score that represents kind of the way that the function's being pulled by either functions that it's calling or calls to it, and then look for. So I'm expecting it to start the score to start positive, switch to negative, and then on the next C file, I'm expecting it to go back to positive again. So the edge that I'm looking for is that place where it switches from the negative direction to the positive direction at the next C file. So this is, since this is a academic conference, this is my formal definition, just so it's in the slides, you can look at it later. I'm hopefully giving you enough information. If you want to reproduce this at home, you can. What this is saying is, I'm looking at all of the references to the function, both the outgoing references, the functions that it calls, and the functions that call it. I'm taking the distance between the functions. I'm taking the log of the distance, multiplying by the sign. So I'm taking the log of the distance, and I get the multiplying by the sign. So that's where I get the positive or negative, and then adding those up and just dividing by the total. So I'm really just getting like a weighted. I'm getting sort of a not weighted, but an average of the log of the distances. The reason I'm doing log, if you're from a physics background, you might think like inverse square would sort of make sense here. It's kind of like that. I'm trying to promote functions that are closer to the function that we're looking at. So functions that are closer to that function are more likely to be in that same module as the function versus functions that are farther away. Inverse squares, it turns out to be just too strongly promotes the functions that are close by. So back to that thing where I said, well, I'm just going to eliminate the external references. The way that I do that is I just say any function call that's over a threshold, I'm just going to throw away for the purposes of the score. I'm not going to count it. And right now I'm using 4K. That's just a number I made up. It sort of seems to work, but there's room for improvement. So the edge detection, basically all we're looking for in this score is that negative trend and a switch back to positive value. A quick note here, if you are trying to recreate this, I'm treating the calls to the function and calls from the function as separate scores. And so if either of those ends up with no score, I'm interpolating it based on the previous function's score. So this is a target binary. This is one that we didn't have source code for. I won't go into what it is, but if you recognize these strings, I'd love to take you out for a beer later and talk about the wonders of this thing. So what we've got here is this is a number line on the x-axis. Every number is a function, and then on the y-axis we have the score. And so the bottom is the whole program, and we're zooming in on a piece of it. You can see, so some of these modules that have a nice characteristic, like sysled has this positive going down to negative, switching back to positive. That's sort of a nice characteristic of what we're looking for. sysltc is another one. The cool part about this target, this is one of the first ones I worked on, and they left in, they had calls to assert. So when you call assert, the compiler will oftentimes put in a string that has the source file name, and so all the source file names were there. What was cool though, not every function called assert, so there were sort of scattered references to these source file names throughout the binary. Sorry, I forgot to mention here that the vertical bars are automatically placed. That's basically our edge detection, our automated edge detection. So on this one, since I had a bunch of these strings of the source file names, I could then look at where we detected edges and where the source file names were, and as long as I didn't have like two source file names within a module that we had specified, I knew we were doing well. So we had pretty good agreement with that. So this is kind of the pulling out the software architecture, right? So it's like, what can you do with it once you have the modules defined? The first thing you can do is just look for common strings within that module range, string references within that module range, and try to sort of guess what the module's name is. In this one, we kind of knew, okay, any of these source file names, that's probably what it is. But I can then, so if I take these module boundaries that I've identified, and then I just create a graph that's the modules, how the modules interact with each other. So it's not just, it's kind of one level up from a function level call graph. I can do this. When I saw this and I was looking at it, I was like, this is really cool. Because you can see some things about the program that pop out sort of immediately to you. And this is like, at the highest level, like immediately after you're disassembling it. This one, I believe that mod 0 here, this unknown mod 0, turned out to be standard library. You can see that like everybody's calling it, and it doesn't call anybody else. It calls this guy, I think, for a timing function or something like that. the you can see, okay, everybody calls the config module. That sort of makes sense that every piece needs to kind of like get some configuration information while it's loading. But there's a really cool like structure here that you can see, where you can see all these modules. So if these are used by the config module, and they aren't used by anybody else, and they don't call out of this subgraph over here. So it's like, okay, well, if I kind of know what the config module is doing, if I know what the interfaces to that are, I don't even have to go in and bother, looking at these modules over here. These are just libraries that support the config module, and I don't even have to go into it. So I think this is cool. It's definitely helping me out in my RE work. Real quick, I'm going to talk about the success metric. So I had to kind of develop people are asking me, okay, well, does it work? And I'm like, yeah, it totally works. And they're like, how do you know? It's like, well, I just know because I can, it's helping me out doing my RE. They're like, well, give me some, numbers. We're a applied physics lab, so we've got to do our metrics. This could be ignorance on my part, but I wasn't really able to find previous work. I wasn't able to find previous work in much in people tackling this problem, but I especially wasn't able to find previous work in how you would measure the performance of solutions to the problem. So I created my own thing. I think if something exists, it's probably in the sort of the signal processing world, maybe in the RF space, but I haven't found it yet. The deal is what we care about. So I'll say when I'm doing this when I'm testing it with data sets with source code that I have, so I can test it on anything really that I get where I can get a map file, or I can modify the build process to get a map file, and then I run my algorithm against it, and it produces a map file of where the object file boundaries are, and then I run this score metric. I don't really care about So here's an example where I've got a big module that we identified as 2 modules. I don't really care about that. What I really care is if it found the edges that were close to the ground truth edges. Again, so this is identifying clusters of functionality, and so, for example, like going back here, this sysp1, we identified this as 4 modules, where it was 1 source file, but it was a giant source file. So we're finding 4 distinct clusters within that source file. So all this to say, the score is sort of just looking at it's not looking at it's looking at did we find the edges that were close to the ground truth, and I don't care necessarily that I had multiple modules there. If there's a gap between the modules, I'm keeping track of that. Sometimes, if we have no score at all, we'll leave a gap there, and so I'm tracking that. But it's basically just measuring the disjoint area, the part I call the underlap between the modules. So these are my results. Got a little data set going here, and I need to just build this out. A couple of different architectures that we're looking at. You'll notice that, like on the PX4 firmware, I've got that ends up with a high gap score. PX4 is a open source flight controller for like hobbyist drones. it has a bunch of functions that are larger than 4K. So those functions end up with no score, kind of as it's written right now. We just don't know what to do with them. So that's kind of the reason for the high gap score there. GNU Chess and the GoodFet firmware. I haven't got to run it on Travis's GoodWatch firmware yet, but I did use the GoodFet firmware. The reason that those scores, or I have those high underlap scores, is they have they'll tend to have accessor functions for global variables. So you'll have a function, so you'll have a C file that's got some global variable defined, and it's got some functions that just like get this global variable, so that it returns that variable, and it's used by other C files, but the functions within that file don't use the accessor functions. They just reference the global variables directly, if that sort of makes sense. So there's kind of no link in the code between the rest of the module and those accessor functions, and they end up getting tacked onto the module beforehand. So that's kind of why they end up with a lower score. But it's all right. So future work. I still think that there's promise for graph algorithms in this space. So I'd really like to try that out. And I think especially if we combine this LFA score with the graph algorithms, we may be able to kind of get a stronger solution there. So I mentioned global data references, global variable references. I think that's definitely a thing that we can work in. I don't know how to, I haven't figured out how we're going to do that yet, and it's going to be sort of like a secondary thing. But definitely if you kind of see a cluster of functions that all access the same global variable, then they're probably part of the same object. Just in the score itself, I think there's a lot we can do. So right now, if the functions have no score at all, a quick thing we could do is just look at a byte-wise similarity score. Is this function more like the functions before it or the functions after it? I mentioned, so I'm using this fixed 4K threshold. I'm not really crazy about that. I think if one thing we could do is just looking at adjusting that threshold and recalculating the scores, and then possibly combining that with edge detection, so you could kind of sweep through a bunch of different thresholds, and then look for kind of which one gives you the best characteristic, and do edge detection that way. Yeah, so that's pretty much it. I'd like to give a quick plug for my employer, APL. We're doing some really cool RE research, kind of in the national security space. If you're a U.S. citizen and that's interesting to you, yeah, please come see me. But yeah, that's all I got. Thanks. Be happy to take questions. I'd love for some mathematicians in the room to throw tomatoes or rocks.
Yeah, I'm not a mathematician, sorry. First of all, great presentation and great tool. I thought about this idea for a long time. First obvious question, which I might have missed, is there an open source code for this?
So I'm planning to open source it, and work is positive about me doing that. So I need to get it cleaned up to where it looks like presentable. But yeah, I'm planning on that. Right, I didn't mention it. It's basically just a Python script in IDA right now. It's a pretty small script, but yeah, planning to. Sorry, okay. I don't have a better answer than that.
Yeah, okay, and second question, did you ever think about extending this to find the actual libraries themselves, I guess you can learn from the statistics of libc, the positive and negative ratio, to understand that this is actually libc, for example?
Yeah, you could do it that way. I think one of the things I'm most interested in is like feeding it in to some of the algorithms that like bindiff uses, say. So it for instance, when you're running like something like bindiff on a large binary, and I do that a lot, where I take bindiff in a standard library, and I say, okay, the standard library is in here somewhere. Go find it. But I think, so for instance, if I can say, I found this code and it looks like standard library, has the characteristics of standard library, then I take that and send it over to bindiff. Then I don't have to go through the entire, I don't have to go through that entire match process. I can kind of speed up that process. So absolutely, I think that's kind of a logical next step.
Okay, thanks.
So that was here in the back. Hi. That was really cool. Thank you for presenting.
Thanks.
You mentioned that graph algorithms are kind of time-consuming and heavy to compute, which absolutely, in my experience too. Have you seen much work in kind of the rooted algorithm space, where if you can find a common starting point for for whatever you're working with, at least in my experience, those end up being an order of magnitude a little bit faster to work with?
I'd say no, and we should. I want to continue the discussion afterwards, because I'd love to talk about kind of any kind of way that we could speed that up. So yeah.
Thanks.
Yeah.
Are you extracting the data from IDA and putting it into an intermediary data format, like a SQL database or anything like that, to speed it up a little bit for analysis?
Right now, it just loads it into a Python data structure that's inside of my script. So you can export it to anything. You can. It's pretty straightforward. So for the graph algorithms, we export to like a GraphViz format. And that's pretty easy, because you basically just iterate through all your cross-references, and then you have a function A calls function B, and you just output A, arrow B. So it's pretty straightforward if you wanted to put it in pretty much any kind of format, I think.
Hi, could you tell me a little bit about how well you think this would scale? We've heard a bit about the tractability, but sort of rough order of magnitude, how big a binary could this technique be extended to in a feasible amount of time? Yeah,
well, the cool part is it's order n, essentially. So it should scale really well. Because you're just, you're basing the score on the number of references, and then you're not, if you did something kind of what I was talking about at the end, with where you were doing some kind of fancy edge detection, that could blow up. But right now the edge detection is also, order n. We're just going through and looking for that delta. So yeah, it ought to scale just fine.
Cheers. Thank you.
Yep.
So I'm going to ask about the local affinity function that you were talking about over here.
Where are you?
Over here.
Oh, hey.
So I'm asking about the local affinity function. You were mentioning how you did it considering the threshold within like certain thresholds. How did you tune that threshold? Because I'm assuming that relates to the length of each of the modules that were constructed by the program, right?
It doesn't limit the module size that's output. It can still output a much larger than 4K module size. It's just for the purposes of the scoring, we say anything that's further than 4K, throw it out. I just sort of played around with it a little bit, and it seemed to be a good number. And I didn't really do any. I didn't do anything further than that. But it doesn't prevent. So if you have modules that are larger than 4K. It's not, you could still you can still detect edges on modules that are larger than 4K.
Okay.
Question back there.
Okay, can we do the remaining questions off stage to
Sure.
stay in schedule? Okay, then thank the speakers again.
Thank you.